So here at X-Ray Coach, we are going to talk about filtration. And we're going to begin the discussion by some factual information. Then I'm going to demonstrate the different parts of filtration. Then we're going to do a demonstration on the board so you can see how it impacts the average photon energy. So let's begin with the factual information. The NCRP report number 102 that begins with minimum filtration in the useful beam states that any generator that's capable of producing 70 keV must have at least 2.5 millimeters of aluminum equivalent for its total filtration. So the total filtration equals the inherent filtration and the added filtration. The inherent filtration is filtration within the X-ray tube, the glass housing, the envelope, the insulating oil, and the collimation mirrors. Typically, this ranges between 0.5 and 1.0 millimeters of aluminum equivalent. The added filtration is materials, usually aluminum, which is placed in the path of the primary beam to bring the total filtration amount up to 2.5 millimeters of aluminum equivalent if operating over 70 keV. So let's take a close look at where filtration is added on this particular machine. Right here, thin layers of aluminum, and it's been added to this equipment so the total filtration can be 2.5 millimeters of aluminum equivalent. This machine can also have a slide that allows the filter to move in and out, but under no circumstance are you to remove that filter. So now let's talk about filtration and how it affects the skin and organ exposure. Filtration reduces skin and organ exposure by filtering out the low energy, harmful X-rays. The primary purpose is to reduce entrance skin exposure to the patient. The effect that filtration has on the average beam energy states that filtration removes or absorbs the low energy, non-diagnostic X-ray photons from the X-ray beam. This increases the average X-ray beam energy, also known as hardening the beam. As filtration increases, the exposure rate decreases. So now let's talk about how filtration affects your patients and the average photon energy of your X-ray beam. So we're going to do a little demonstration so that I can show you how it actually functions. So now remember that our X-ray beam is heterogeneous, which means that the energy level of each photon is different. But if we have a KVP that's set at 80 KVP, we can expect some of each photon to be slightly different. Some of the photons are going to be at 0, and some of the photons are going to be at 80. So what do we really want to accomplish with a filter? Well, we want to be able to absorb the low energy X-ray photons because they're not going to do anything but be absorbed in the skin. So now let's go ahead and do the demonstration on how this actually works. So let's say, for the sake of just an example, this one is a measure of 80. This one's a measure of 10. This one is 70. And let's say this one measures 10 and this one measures 80. If I took all of those numbers and added them up, they would add up to 250. So now let's find the average photon energy. And we would find that by dividing that by 5. So right now we would say our average photon energy for this particular X-ray beam is 50 keV. So now if we let the filter do its job, and that is to remove or absorb the low energy X-ray photons, we would take those out. And now we need to figure up what our average photon energy is. So if we added up all these numbers, they add up to 230, and we're going to divide it by 3. So now our average photon energy is worth 76.66 keV. So just by the use of the filter, we have increased our average photon energy to 76.66. So what does that mean to our patients? Well, that means that the overall skin dose decreases, the average photon energy goes up, and that overall is going to produce a longer scale of contrast.